The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Today I'll begin by talking about a subject that we were just getting to at the end of class last time, and that will be electrolysis. And this is an interesting topic. One of the examples of electrolysis that is commonly used is that which forms the basis for the so-called Dow process. Here what I'm representing is a container, and a container that would be used to house molten magnesium chloride. So if you take magnesium chloride, which is a typical salt, and get it hot enough, then it will become liquid. And when it becomes liquid in the melt, what you can do is carry out a non-spontaneous reaction by applying an external voltage. So the idea is that this is some supply, some source of a potential difference, and you can take a positive electrode and a negative electrode and immerse it into the melt, and if the potential is sufficiently great, you can force a non-spontaneous reaction to run, because overall the reaction will be spontaneous when you factor in the potential difference of the external source. And in this particular case, the reaction that would be taking place is as follows. At one side, we would have magnesium 2+ ions being reduced to, at this temperature, liquid elemental magnesium, so metallic magnesium at one electrode. And at the same time, at the other electrode, what would be taking place is the oxidation of chloride ions, which are two of which counterbalance the magnesium 2+ in the salt magnesium dichloride. And we put in a couple of electrons. We're oxidizing chloride to Cl2, which would be bubbling out as a gas at the temperatures of this melt. So you initially would have this molten salt. You'd immerse your two electrodes. You'd apply an external potential, and if that potential is great enough, then these two reactions start taking place at the two electrodes. And you can see that in order for this to happen, chloride is being oxidized, and so we can see then that this must be the source of the positive end, the positive electrode, and electrons will be going this way and going down here, and when they collect in this electrode on the left, they are used to reduce magnesium 2+ to liquid magnesium. So that's an electrolysis reaction in which something that doesn't want to happen, namely the reduction of magnesium 2+ to magnesium 0 by chloride ions, that's non-spontaneous, and we're forcing it to happen by applying this external potential. And just how great must that external potential be? Well, Christine, could you locate for me on the table there the potential for magnesium 2+ plus 2 electrons going to magnesium, and the potential for Cl2 plus 2 electrons going to 2 Cl-. Note that our standard potentials that we defined last time relative to the standard hydrogen electrode are always written as reduction potentials by convention. So what is it here? Can we zoom in on it? Zoom in on your finger. Okay, by the way, I had her do this in part because I wanted to draw your attention to this table that is in one of the appendices of the textbook. So it's in the back. There's an abbreviated form of this table right in chapter 12, which you should be reading. But when you want to find a standard potential that's not in that abbreviated table, you will now know that you can go to your appendix to find that reduction potential. So, Christine, please read out to me the value for the chloride. Is that the one you have there? Yep. Plus 1.36. Okay. And this is positive of the standard hydrogen electrode, showing you that Cl2 is an oxidizing substance. And then what about the magnesium plus 2 electrons? Minus 2.36. Remember I mentioned last time that elemental sodium was around minus 2.7 volts, so it was a very strong reducing agent. Magnesium is also a very strong reducing agent. Chlorine is an oxidant, so clearly the direction of spontaneity in this system is for magnesium metal to be reducing Cl2 to make chloride ions, and that's why the form of the salt that Henry Dow, as a young man, was extracting from the briny marshes near his home in Michigan, and later founded the Dow Company on the basis of chemistries like this. That's how you found it, as magnesium 2 plus Cl2 2 minus. And so overall, if you reverse the sign of the anode reaction and add it to the cathode reaction, you're going to see that this one is non-spontaneous by an absolute magnitude of 3.72 volts, which is this difference between these two values, this absolute difference in potentials. So that means that we're going to have to apply an external voltage of greater than 3.72 volts positive in order to get this thing to run and to be able to get gaseous Cl2 bubbling out, and in order to get liquid molten magnesium to be formed and separating from the molten magnesium chloride. So that's a large external potential. That's the price that you have to pay to make this non-spontaneous reaction go. And that's the minimum price. If we could just briefly switch to the Athena from the document camera. I want to mention this one word, overpotential. You'll see an explicit definition of the word overpotential given in my notes and in your book. But what overpotential is in fact, it's a number, and it's the amount of voltage that's greater than this non-spontaneous cell potential that you have to apply in order for the reaction really to start kicking in and working. So it's, in practice, you choose maybe a couple of platinum electrodes and you dip them into the thing that you want to electrolyze, and you apply an external potential, and in practice that external potential is something much greater than the cell voltage of interest, and sometimes it's even a large amount in excess. And the reason has to do with the barrier to the reaction that's introduced by the way that it takes place at the interface on the surface of these electrodes. So you have to apply some overpotential. That's energy that you have to put into the system over and above the inherent energy of the electrolysis to make it actually work in practice. And so the substance that we would most like to be able to electrolyze is water. Because if you think about it, electrolysis of water would produce hydrogen and oxygen. And then we can have those in our fuel tank, and we can go ahead and let combustion take place, which produces what? It would produce water. Okay, so you get a beautiful complete cycle if you could do a good job of electrolyzing water into its components, H2 and O2. All right, and the reason that that's difficult is because you have to put in energy somehow in order to make that non-spontaneous reaction go uphill. We would like to make that the basis for the hydrogen economy. Okay, I really love Iceland. This is my favorite country, I think, although I've never been there. And it is because they do this reaction. They do this electrolysis of water every night so that they'll have hydrogen and oxygen for combustion purposes the next day in their buses in the city, and they're actually doing this. And why are they able to do that? Well, their special location on the planet gives them a lot of free electricity that they can use to run the electrolysis of water to make hydrogen and oxygen every night, and then they can combust that in their buses, and you essentially you have free hydrogen, and it's not a problem. And they're getting, in places like Iceland or other places in the world where you have freely available energy from geothermal sources or from hydroelectric power, then you can do that. You can use that energy, that electricity that's free that the Earth is just giving you to go ahead and carry out the electrolysis of water and make hydrogen that way. And we would like to be able to do that using photochemistry. So there's one possible way to get the positive holes and the electrons apart is to use H-nu. Okay, so a photon can impinge on a material and lead to the separation of charge in what's called a photovoltaic device. And if you can interface a photovoltaic device to a couple of electrodes that have surfaces that are appropriate chemically for minimizing the overpotential, then you can use light coming in from the sun to make electrolysis of water happen to get hydrogen and oxygen from light that's coming in incident on the Earth. And so one thing that is currently ongoing research in a partnership at Caltech and MIT, and I'm involved with this. This is Professor Nocera here. And you'll see him walking around, this furry face, walking around the hallways at MIT. And he's an amazing guy. And if he does what he's trying to do right, he's probably going to be the next one in our department to win the Nobel Prize. So Professor Nocera is currently the professor of chemistry and professor of energy here at MIT. He's the energy professor. And he's a lot more voluble and vigorous, I think, than I am. He's really bouncing off the walls with energy. And that's good because the technical challenges that we have to surmount in order to be able to use sunlight to carry out water oxidation, water electrolysis, are very great. But they come down to chemistry and to molecules. Okay? Starting on Wednesday, we're going to enter a part of the semester in which we treat the subject of bonding in chemistry in quite a bit of detail. We're going to be talking about molecular orbitals and things like that. And if you get a good understanding of molecular orbital theory and electronic structure and the shapes of molecules, you may be able to contribute to this problem by helping to design molecules that can go on the surface of the electrodes. And the purpose of those molecules is to reduce the overpotential for water electrolysis with sunlight as the source of the electrons and the holes. And this man's entire life is defined by one number, and that is the overpotential. Okay? So we're making electrode molecules that will bring down the overpotential and give us a free source of clean energy from water. Okay? So 1 week from today, you're going to have a little introduction to undergraduate research here at MIT. We're going to have some visitors who will come in and talk to you about the 5.301 subject, which is given during IAP. And the people who successfully complete the 5.301 subject are then guaranteed a position in a research laboratory in chemistry as an undergraduate research opportunities program student. So if you want to get involved in the molecular chemistry of renewable energy, then you might want to make sure you're here on time for class on Monday, and you'll get that introduction, and you can think about what to do in terms of 5.301. Now, I want to bring you up to speed on some more important concepts that pertain to electrochemistry. So let's talk about electrical work. Here I want to make an analogy to the way that electrons can do work when they fall through a potential difference and experience a potential difference. I want to make an analogy between that and the way that things go downhill by virtue of the force of gravity. Okay, so you can think of a waterfall of electrons flowing from a place of high potential to a place of low potential if you want to get an idea for our expression for the way that the free energy of reaction is related to electrical work. And it is a potential difference. It's the total charge that is passed multiplied by the potential difference through which the charge is passing. Okay, we've been talking about this potential difference and calling it E. If it's a standard potential, then we'll use the superscript 0 or the little degree symbol for standard. Now we want to know what is the total charge. It's going to be negative n times the charge on the electron times n sub a, which is Avogadro's number. And we're going to be interested in getting the total charge expressed in terms of a quantity per mole. Actually, we're going to express it in coulombs per mole. And so we combine E and Na together, and this is one of our fundamental constants. This is Faraday's constant, and you'll remember that that's approximately 96,485.3 coulombs per mole. Okay? That's Faraday's constant, and we'll use that as our way of expressing charge here. And so we get the important expression delta GR is equal to negative n Fe. Okay. And we'll use that a couple times today in getting access to other quantities. And what is n? That's going to be the stoichiometric number of electrons passed in the half reaction of interest. So I'll show you a couple of examples of how you figure out what n is in this expression. Okay. So it's the total charge times the potential difference. One of the things that this is useful for is for finding a relationship between an equilibrium constant and a standard cell potential. And we can do that by recalling from chemical equilibrium the expression that delta G is equal to minus RT ln K. And now we have a new expression down here for delta G. Okay? And let's go ahead and insert that, and we'll see that NFE is going to be equal to RT ln K. And so we can just rearrange that and solve for our quantity of interest here. We're going to see that the equilibrium constant K is equal to an exponential of NFE divided by RT. And this should be for a standard potential, and then this is the equilibrium constant, that special value of Q that applies when the system is at equilibrium. So let me put the little superscript up here to make it clear that we are talking here about a standard potential. So the idea is then, if you have a reaction and you can express it in terms of half reactions, then you can go to our table in the appendix, if those half reactions happen to be in the table, and then you can calculate the value of the standard potential for the cell that would be comprised of those two half reactions, as we described last time, and then given these other quantities, we can calculate the equilibrium constant for the reaction. So it's a useful thing to be able to do. You take a standard cell potential and then take a temperature like the standard temperature 298.15 K, and you have your value of F that I gave you, and you can look up, of course, the value for the gas constant, and you have N from the stoichiometry of the number of electrons passing through this potential difference, and then you can get K, and you see that this equilibrium constant K goes up exponentially as the standard cell potential increases. So that's a quite interesting relationship too, and I'd like to give you an example of how we can use this. So let's consider a possible reaction of this sort. This reaction, of course, as you would see in the table of standard reduction potentials, is assumed to be taking place in dilute aqueous solution. Okay. Actually, if it's in a standard state, the concentrations of the ions will be taken to be 1.0 molar, which that's the concentration, standard concentration. One thing that I regret about my lecture on Friday and about my lecture today is that I'm not really talking too much about molecules and molecular shapes and what these things actually look like in solution. But normally when you have metal or metalloid ions dissolved in aqueous solution, there's some number of water molecules that are interacting directly with the metal ion. So it's not just, so to say, a naked metal ion, but it's bonded to water molecules in solution. And this is through the type of Lewis acid, Lewis base chemistry that we talked about earlier. There would really be some number of water molecules bonded here. And we'll look at so-called coordination complexes in quite a bit more detail in the upcoming section on chemical bonding. But this is how you'll find it typically written in a book, and that's not representative of the structure in solution, which you do need to know in order to have a real good understanding of the system. And we're going to consider the possibility that indium may react with uranium to provide indium 2+. So we're going from trivalent to divalent indium, and the source of that electron is the uranium 3+ ion going to the uranium 4+ ion. Okay, so there's a hypothetical reaction that we want to consider, and we're going to need to be able to express that in terms of half reactions. And one of these half reactions is simply indium 2+ plus an electron. Sorry, indium 3+ plus an electron going to indium 2+. And similarly, it's a little distracting. What was that? Over here we have uranium 3+. I'm writing both of these as reductions, as you will find them in the table. 4+ plus an electron going to uranium 3+. Okay, so those are our two half reactions, and Christine, can you zero in on them? Yes, you're doing that already. Thank you. Minus 0.49 for indium. Okay, and then when we look at uranium, these are arranged alphabetically. There is
They by potential.
here they are in alphabetical order. So they can be in the tables. They can be arranged by potential, or they can be arranged alphabetically. And sometimes it's easier to find a potential by taking advantage of alphabetization. And so if we can focus in on that, and you'll see that the 4 plus going to the 3 plus is minus 0.61. Okay, and then you'll remember that to find the standard cell potential, E0 of the cell is going to be equal to E0 of the cathode minus E0 of the anode. And what we can see here is that this reaction is going to proceed spontaneously as written, because in going from left to right as written, uranium plus 3 is going to plus 4. So uranium is the reducing agent, and it is a stronger reducing agent than the other possible reducing agent, indium-2 plus, because it's more negative than indium-2 plus. And how much more negative is it? It's more negative by positive 0.12 volts. And we therefore, because this cell potential is positive, we know that this reaction is spontaneous as written. And it's positive by 0.12 volts. That's a spontaneous reaction. And now we have all the information that we would need in order to get the equilibrium constant for this reaction. So we know that in terms of standard potential, it's 0.12. So let's see here if we can just calculate this. Bye-bye, Professor of Energy, for now. All right, I'm going to take this and zoom it a little bit. Okay. We're going to put in Faraday's constant of 96, what is it? What did I say? 485.3. And also we're going to need the gas constant. Everyone remember the value of the gas constant? 8.31447. Okay. And now, if we look over at our relationship between the equilibrium constant and the free energy over there, which allowed us to get, we take a free energy, we convert it into a standard cell potential, and now we've got it. So we should have that. What we want to solve for is an exponential of NFE. N is 1 here because in both cases we have 1 electron being transferred in the half reaction. So we have the exponential of F times 0.12. Sorry, is that right? Yeah. 0.12. And then that's divided by RT, and so we have R times 298.15. Okay, and let me just make sure I get back over here and get another parenthesis in there and see what it is. Okay, so our equilibrium constant for that reaction with a separation for the standard cell potential of only 0.12 volts is about 106. So the equilibrium constant says that concentration of these ions multiplied together divided by the concentration of these ions multiplied together is 106 based on the information contained in the half cell potentials. So that was pretty cool. And we will now go ahead and talk about another relationship that we can get. So over there, I was able to give you that relationship between equilibrium constant and standard cell potential by remembering something from chemical equilibrium. And now we're going to do that again, and we're going to remember that delta G for a reaction is equal to delta G naught plus RT ln Q. Okay, so that's something that you should remember from your studies of chemical equilibrium. And the neat thing is now that we know that we have another relationship for the free energy of a reaction that's related to electrical work. We got that up there. So now we can go minus NFE. And notice that what we're doing here is we're considering what happens when we perturb a system from equilibrium conditions. And when might that happen? Well, I showed you how to set up a galvanic cell last time, and I showed you how to calculate its standard cell potential. That you could do that. You could measure the standard cell potential by using externally a voltmeter. And as long as you didn't let the reaction proceed to any significant extent, then you'd know the standard potential for that cell. And what we're going to do now is we're going to say, okay, let's let the reaction proceed. Let's let a battery become discharged, for example. And let's ask, as the reaction is proceeding, we might want, for example, to be able to make a plot of the potential at any particular extent of reaction. Okay? And in order to do that, we'll develop this equation here. That shows how the potential at any particular point along the reaction going to completion is related to the standard potential and all I've done now is substitute minus NFE and minus NFE0 in respectively for delta G and delta G0 for the reaction. And now I want to go through and divide by minus NF. And when I do that, I'm going to get E is equal to E0 minus RT over NF ln Q. And this equation is very central to electrochemistry. It is the Nernst equation. And you will be able to use the Nernst equation to predict how systems will behave when they are perturbed from equilibrium. And one example would be that of a battery discharge, like I was mentioning a moment ago. So send this board up to the top. And so let's kind of pick some arbitrary material out of which to make a battery. Okay, and we'll use the Nernst equation to get information about how it will discharge. And let's consider the following cell. It will be one in which the two half reactions are as follows. Iron 2 plus 2 electrons going to Fe, metal. And the other material will be cadmium 2 plus 2 electrons going to cadmium metal. So now we need the two reduction potentials, standard reduction potentials, for iron 2 plus which is coordinated in aqueous solution to 6 water molecules in an octahedral array, but we'll get to that later. And I can see the equation but not the value. And there it is at minus 0.44. Is that what it is? And now we need cadmium 2 plus going to cadmium elemental form. And we see that that is up there at minus 0.40. Is that right? Minus 0.40. Okay, so both cadmium metal and iron metal are negative of the standard hydrogen electrode. So they're both reducing systems, as it were. And however, we see that iron is more negative. And since iron is more negative, if we set this cell up, if we have a piece of cadmium on one side and a piece of iron on the other side in this cell, then this piece of iron metal is going to be providing the electrons in this system when we go in the spontaneous direction. Okay, so the electron flow in the external circuit will be from the iron metal electrode to the cadmium metal electrode, and things happen in solution as we've discussed, but that makes iron the anode. And for the reaction going that way, as we would have set it up, then we have a standard cell potential, E0, of positive 0.04 volts. Okay, and now in order to apply the Nernst equation to answer a question about this battery, and this battery is not a high voltage battery, it's only 0.04 volts. It's not high voltage at all. So you probably wouldn't use it for a battery unless you really only needed a small potential difference in the first place. But nonetheless, we want to know how can we use the Nernst equation. We can say, what's the voltage? What is E at 80% completion? Okay, so that's the type of question we can answer using the Nernst equation. What is the potential drop to from an initial positive 0.04 volts when the reaction is 80% complete? Okay. Under standard conditions, we have 1 molar solutions on both sides of the ions. So in this solution, we would have 1.0 molar cadmium 2 plus, and over here in this solution, we've got 1.0 molar Fe2 plus, because those are the standard conditions, as you will see written in the header to that long table in your appendix, because you have to define standard conditions in order to have a standard potential, and the standard conditions are 1.0 molar of the ion respectively in solution. Okay, so at 80% completion, what will happen is we will have gone in terms of we're producing iron 2 ions in solution. We're producing them in solution as the electrons flow through the external circuit, because the piece of iron metal is the anode. And so what we're interested in here is Q, and that is going to, I'm writing backwards. Pretty soon I'll be writing straight down or sideways. Okay. In the reaction as written in the forward direction, we are producing Fe2 plus ions such that we can define our Q at this 80% completion value as 1.8 molar divided by 0.2 molar, and that's equal to, of course, just 9. Q is equal to 9. So we have our T will be 298.15 Kelvin. Our F is our number of coulombs per mole, that is the Faraday constant. And in this case, because in the half reactions you have 2 electrons rather than 1 being transferred, N is equal to 2. So if you plug in now, you have E0 is 0.04. You have RT over NF ln of 9, and that will give you the potential at 80% completion, which is somewhere in between 0.04 and 0, okay, as this battery is discharged. So if you want to model the way in which a battery is discharged, you can use the Nernst equation for that purpose. But there's another type of cell that is interesting that you can also describe very well using the Nernst equation. And this will be what is called a concentration cell. Concentration cells are pretty neat. In a concentration cell, you set up a potential difference with the same electrode materials on both sides, just different concentrations. So if I were writing this in terms of the type of diagram I used last time, I could show you that we could connect 2 beakers with a salt bridge like that, and we could have electrode materials here dipping into solution on both sides. And in solution, on one side, we're going to have SN2 plus divalent tin ions, okay, at a concentration of 0.01 molar. And on the other side, we'll have SN2 plus at a concentration of 0.10 molar. Okay, so this one on the left is dilute by a factor of 10. Okay, that one's the more dilute one by a factor of 10. And we can ask what kind of a voltage is set up as a consequence of just simply having different concentrations of tin ions in the 2 beakers. And we can ask in which direction would the electrons flow in a system like this. Okay, well, in this reaction, we go from, the system wants to go from a state where tin 2 plus ions at 0.10 molar go to the beaker where we have SN2 plus ions at 0.01 molar. So we have a potential set up here that is similar to the way osmosis takes place. The ions want to move from a region of high concentration to a region of low concentration, and the system would come to equilibrium at that time when the concentration is the same on both sides, and then there would no longer be any potential. The value of E0, E naught for this cell is equal to 0, because we have the same electrode, the same half reactions that would take place on both sides. So E0, E naught is equal to 0 volts in the concentration cell. And which way do electrons go? Well, here's how you can think of it. We'll have the electrode material can be made out of tin on both sides. And since tin ions are going to appear in solution on the dilute side, they're going to jump into solution from the electrode itself. So a tin atom that's a piece of the metal on the surface of the electrode will jump into solution as tin 2 plus, increasing the concentration of tin 2 plus on the dilute side. And every time it does that, we get 2 electrons racing through the external circuit, going over here, where those 2 electrons can be used to reduce tin 2 ions in solution that become a new tin atom on the surface of the electrode on the right-hand side. So that's physically what happens to equilibrate the concentration of tin ions on both sides as a function of time. And so what we can find is that these 2 values of the concentrations go into determining our Q in the following way. See if I can get Q written properly. Okay, we've got Q of 0.1 because the tin ions are going from a place of high concentration to a place of low concentration, and electrons are traveling through the external circuit, defining the cathode and the anode in the direction that I mentioned. The electrons are coming out over here, so the dilute side is going to be your anode. And we have N equal to 2 in this particular case because it's a 2-electron process that converts tin 2 plus into metallic tin. So you can take these numbers, plug them into the Nernst equation, and where you have E naught is equal to 0, N is equal to 2, T would be 298.15. We know the Faraday constant and the gas constant. We have Q is equal to 0.1, which is our concentration ratio between the 2 sides. And when we solve that, we're going to find that some small voltage is produced initially at this set of concentrations. Okay, so I hope that in the last couple of lectures today and last Friday, I've hammered home the relationship between electrochemistry and energy. And next time we'll go forward in talking about molecular structure and see how that's going to play a role.